Swayam Prabha. Digital India. Educated India.
In this lecture, we continue to discuss on the wind tunnel design issues related to subsonic wind tunnels, and then we would also initiate a discussion on supersonic wind tunnels. In the previous lecture, we had discussed about the section loss coefficient, and you may recall that we referred to the test section dynamic pressure while discussing about section loss coefficient, which we called as KLT. And we also showed that the summation of the KLT contributions coming from the different components of the tunnel, when we take a reciprocal of that, that gives us the energy ratio of the tunnel. So, larger the energy ratio, the more efficient is the tunnel from energy point of view. So, this is the planform view of the closed circuit wind tunnel that we were discussing about, and here you see a very rough representation of a numerical simulation which was done for a typical closed circuit wind tunnel, where you can see the flow features. Essentially, it is representing the pressure variation around the tunnel, and you can figure out that this is the test section of the tunnel where the flow is most accelerated, and therefore, the pressure would drop significantly, and then it gradually recovers as it moves into the diffuser, and so on as it moves through different components of the tunnel. Now, in this table, we are going to look at some typical figures of the KLT terms for each one of the components of the tunnel, and then we will try to also assess what is the total loss which is incurred in each one of those components, which finally sums up to 100%, and then trying to assess the ER, the energy ratio, based on the summation of the KLT terms. Starting from the test section jet, so that incurs loss of around 5% of the total circuit losses, and keep a watch on the KLT figures. By definition, KLT is the stagnation pressure loss across the component by the dynamic pressure which is there at the test section. As you move into the diverging section after the test section, you can see that the loss is significantly larger than what you have in the test section jet, and that accounts for almost 4 times the loss, about 21%. That happens to be one of the most large losses. A still higher loss is incurred at the corner here, and remember that here in the test section the flow was at the highest possible velocity within the wind tunnel circuit, and then it was gradually slowing down in the diffuser following the test section and then turning. So, the flow is still at a fairly high velocity, and incidentally the losses that are being incurred are also on the higher side. Of course, as you move it through the diffuser, the losses are in general higher because the flow is going through an adverse pressure gradient, and there is always a tendency of minor flow separation occurring as the flow moves through such an adverse pressure gradient. Then it moves through several sections, the cylindrical section that follows beyond that, where the losses have reduced, and then again you see that at the corner the losses are similar to what happened here. Then it moves into another cylindrical section which also acts as a transition section, moving from a rectangular to a circular section. The losses are lower. Then the divergence following the fan, the losses are coming down here. The flow has diffused already quite significantly. It is getting slower, and correspondingly the losses are also reducing. So, in general, the flow velocity, the average flow velocity in a section will also influence the extent of loss. Sections where the flow velocities are on the higher side would also be responsible for higher losses. As you can see, when the flow is moving much slower at these corners, the losses have come down significantly compared to what they were when the flow was moving faster. And then the final cylindrical sections here and here, where it is already very slow, the losses are on the much lower side, and finally, the cone in the sense of the converging section. So, that more or less gives us an assessment of the total loss distribution over all the components of the tunnel. And finally, based on the KLT summation, you get an energy ratio of 5.45, which is fairly good. We will do an example calculation now. So, we will do a sample calculation to find out how we can assess the section loss coefficient for a diffuser experimentally. So, by experimental means, can we make certain measurements and assess what kind of losses are being incurred. If we can set up such a procedure, a similar approach may be followed to assess losses for other components of the tunnel also, if it is sufficiently generic in nature. So, let us try to discuss on that. So, to begin the calculations, what we will do is we will look at the test section. Let us say the flow is moving from left to right along the test section, and the test section, we will assume some dimensions for the test section. Let us say it is a 60 centimeter by 60 centimeter sized square test section. So, that gives you a 0.36 meter square cross section of the test section. So, if you were to take a section here, if this is a plan view, then you would actually get to see a square section. So, it measures 60 centimeter. On all sides, forming a square cross section for the flow to move. And let us say that the test section velocity is 30 meters per second. So, with these values, additionally the density, let us assume it to be 1.2 kg per meter cubed. Now, we are ready for doing the jet power calculation. So, jet power by definition, as we have learnt already, is half rho a v cubed. So, if you just plug in these values, what do you get? You get 5832 watts. So, that is about 6 kilowatts of power, and then of course, energy ratio, we are just recalling the definition. The PT that we just worked out fits in there. You have to divide it by the total loss, the power that goes into the losses, but we do not know this yet. We of course, do not know the sum total effect here as well, but we are just trying to find out how we can work it out for each component, and we have chosen a diffuser for doing the calculation. So, when we go component wise, a section loss coefficient, we had originally defined it as KL, and then we converted it into KLT. So, KL, how is it defined? For a local section, half rho VL square comes in the denominator, the dynamic pressure. So, what you have on top is the loss in stagnation pressure, and remember that what we mean by VL square is based on the entrance of that section. That means, if you have a diffuser, the dynamic pressure that you have at the inlet of the diffuser, that is what we mean by that nomenclature. So, let us say flow is moving this way, it moves through the diffuser, and the static pressure in general will rise. Let us mark this as station 1, this as station 2. So, you can have static pressure ports at the 2 points, and then if you take a static pressure tube from there with a wall port and then you set up a manometer where you provide the pressures. What will you notice at the manometer end? You will notice a difference in height of the manometric fluid. Let us mark it as delta H. Okay, we will come to that later. Additionally, you can put in pitot-static tubes, and what they will provide you is an assessment of the velocities, V1 and the V2. Now, as far as the two sections are concerned, V1 is around 30 meters per second, which is we are assuming that the velocity remains constant all through the test section, and it enters with the same velocity into the diffuser. So, V1 is 30 meters per second. We do not know V2, but which is at the exit of the diffuser, but from continuity equation A1 V1 is equal to A2 V2. We are assuming density to remain constant at these speeds, and therefore, V2 will turn out to be, what is the area at the downstream section? We do not have a definition for that. Let us assume A2 by A1 to be 2, which means A2 is 0.72 meter square, and that gives you a 15 meter per second velocity at the exit of the diffuser. Now, if you look at the stagnation pressures at the two stations P naught 1 and P naught 2, then how can you work them out? Let us write down the representations. So, the dynamic part we can write down. The representation will be something like this, so many pascals or newtons per meter square. This is the pressure, the stagnation pressure at 1. Similarly, you can work out the stagnation pressure at the second point. So, that will be P 2 plus 135 pascals or Newton per meter square. So, you should be comfortable using both the units. Now, obviously, because there are viscous losses, there will be a loss in stagnation pressure. So, P naught 1 will be greater than P naught 2. So, when you find out the difference, it will be like P naught 1 minus P naught 2 will be the drop in stagnation pressure across the component. So, finally, when it comes to the K L for the diffuser, what will be the expression for it? Let us plug in the expressions. And the dynamic pressure will be based on what comes into the section. So, that is based on 30 meters per second. So, that is finally P 1 minus P 2 plus say 405 by 540. So, the 405 comes from the subtraction of 135 from 540. Once we are done with this, let us look at the delta H that we had at the manometer end. So, let us say the delta H was 4 centimeters. How can we find out the P 2 minus P 1 based on the delta H? We use delta H, we multiply it with the manometric fluid density, let us say it is water, that means 4 centimeter column of water into G. So, that is 4 by 100 into 1000 kg per meter cube into 9.81 meters per second square. That would give you a pressure difference of 392 pascals. Now, you plug it into the K L expression. So, it will be minus 392 plus 405 by 540, it comes to 0.024. That will be the value of your KL. If you want to find out KLT for the diffuser, it would really not matter, because by definition KLT is KL into QL by QT, but here QL and QT are going to be identical, because the QL happens to be based on 30 meters per second, which is the same as the test section velocity. So, this is as good as KL itself. Now, if you recall that in the table of values that we had shown, there the KLT value was slightly higher than this. The KLT value was 0.0391. That means that particular tunnel, whatever design we were looking at, had a slightly higher loss coefficient. So, if we were to ask the question that what if for this tunnel itself the loss coefficient at the diffuser end was 0.0391, then what would be the corresponding change in the delta H, for example? How would it be reflected in the delta H? Well, if you want to do a backwards calculation, then we start from KLT equal to 0.0391 and we find out that P1 minus P2 based on that would be a value like this, which is minus 383.9 Pascal, assuming that we keep all the other things the same. That means, the test section velocity, the cross sectional dimension, etc., we keep the same as what we did for this particular calculation. So, P1 minus P2 is different here. Let us put it the other way, P2 minus P1 is then 383.9, about 384 Pascal, while for the case that we did, it was 392 Pascal. So, there is a slight change in pressure, and then how does it reflect in the delta H calculations? Delta H is 383.9 divided by the rho and G. So, what does it give you? It gives you a value of 3.9 centimeters. That means, only for 1 millimeter change in the water column height, you can see a corresponding change in pressure of this order. And how does it reflect in the KL calculations? Where the pressure is higher, you get a KL of 0.024. Where the pressure is lower, you get a KL which is 0.0391. That means, as the loss coefficient is increasing, the pressure difference between the two sections is reducing. There is a lower gap between the static pressures. It is because there is a loss in static pressure basically. If there was no loss at all, then what would be the situation? The situation would be that P2 minus P1 would then be 405 Pascals for the problem that we are solving. So, this is an ideal case without any losses incurred in the diffuser. So, we just understood how to put the things together based on a simple measurement in the test section by means of static pressure ports. And using this approach, you can actually try to work out section loss coefficients for any other section of an open or closed circuit subsonic wind tunnel. Let us move on. So, here what are we looking at? We are looking at how the static pressure varies along the tunnel circuit. Again, we have to keep the picture, the plan view picture of the tunnel that we have been looking at for quite some time in mind, the closed circuit tunnel. The power input to the wind tunnel comes from the axial fan, and the fan is the source of the power. However, the fan as well as the straightener section, in a combined manner, it provides the rise in pressure as the flow passes through the section. The increase in pressure provided must be equal to the pressure losses which are incurred all through the other sections of the tunnel. And this happens when it is operating steadily. That means the power input at the fan end is exactly balanced with the power losses in the remaining components of the wind tunnel. That brings in an equilibrium, which we are stating as a steady flow operating condition. Now, if you were to look at how the static pressure varies along the tunnel circuit, then we have to imagine that plan view in mind, and we recall that the test section lies here. The flow is most accelerated at the test section, and therefore, we are finding that the static pressure is lowest at this end. Once it crosses the test section, it gets into the diffuser and the static pressure rises, but there are two lines that we are looking at over here. The dotted line is the ideal static pressure distribution in a loss free tunnel. That means, practically in this tunnel you would not need to feed any power through the fan at all. Once it starts running, it runs perpetually. It is more like a perpetual motion machine, but then that does not happen in reality. So, we have to get closer to the reality. So, what does reality say? It says that the actual static pressure variations fall below what it is predicted according to the ideal theory, because losses are being incurred in every section, and that reflects through drop in the static pressure that we already saw through the calculation that we were doing a few minutes back. So, the realistic static pressure distributions fall below the ideal static pressure distribution downstream of the test section. It carries all the way through up to the fan section, where the fan jacks up the static pressure and puts it beyond the ideal static pressure distribution. So, here as you can see, the actual static pressure distribution is overshooting that of the ideal, and then as the losses start accruing, gradually it again starts falling closer to the the ideal static pressure distribution, and by the time it is at the test section, they are balancing each other. So, this is the actual story compared to the ideal story. If you have a better tunnel, you need a smaller jump across the fan, and you can still sustain the flow, because you are incurring less losses and therefore, less drop in static pressure. Let us have a quick look at the optimum running conditions for the fan. We have taken figures from a computational study which was done for a large facility in the form of a closed circuit wind tunnel, and some of these figures are representative of that simulation, but we are going to interpret the values through a kind of a qualitative approach, and we will try to appreciate the main points which these curves are trying to represent. We know that the fan provides necessary power and rise in static pressure to keep the tunnel running. If you look at the fan's characteristic, then what we have to keep in mind is that the fan can operate at different RPMs. For example, this is a fan characteristic given by the red line, which is for a 600 RPM case. Again, this is another characteristic when it is running at 400 RPM. So, these curves are actually representative of the fan shaft power. That means, how much power has to be provided to the fan to make it operate at 600 RPM. And as you can see that there is varying volumetric flow rate over which the fan can operate with the same RPM. And you can see that over the changing volumetric flow rate, to maintain the same RPM, how the fan shaft power will be changing in terms of kilowatt. So, obviously, if you are operating somewhere here, the power requirement will be pretty high, and therefore, you may like to be at a lower point somewhere here. Okay. Again, the pressure rise across the fan is another issue that you have to keep in mind. The total pressure rise across the fan is again indicated along this axis in terms of pascals. So, that is the rise in static pressure that the fan can bring about. You would like to be lying high, because you can bring in a large jump in static pressure across the fan, but then again you have to remember that in that case you may be consuming more power, and therefore, if you drop a little bit in terms of the pressure, then the power requirement also comes down. But then again, we are not running the fan without any purpose, we are running it to drive the tunnel. So, we have to also look at how the tunnel characteristics look like. So, that is down here. So, if you look at this line, this is the pressure drop inside the wind tunnel, and therefore, as you can see, as the volumetric flow rate increases, that means the test section velocity is increasing, the pressure drop also is going to increase within the tunnel. Most importantly, you have to find an operating point where the pressure rise across the fan matches with the pressure drop inside the wind tunnel. So, when the fan is operating at 600 rpm, for example, this is the operating point where the characteristic of the fan matches with that of the tunnel, and that becomes the operating point. So, that is the point at which you get the appropriate volumetric flow rate, and that basically decides the test section velocity. If you operate the fan at a different rpm, for example 450 rpm, then this is the pressure rise across fan line for that rpm, and then you find a different operating point for that rpm of the fan, and as you can see, the volumetric flow rate reduces, and therefore, the test section velocity will also reduce. So, this is the way we interpret it. So, we will just look at this write up saying that the fan can run at different rpms, and with change in rpm, the fan characteristics can be plotted. So, you have the volume flow rate versus pressure rise across the fan. The fan shaft power, which is delivered by the electric motor, increases with fan rpm, which is quite intuitive, and additionally we have the fan efficiency plotted here at different rpms. Incidentally, at least for these rpms, it does not vary very dramatically. It hovers close to about 90%, which is a fairly efficient fan, and it only spans over different ranges of volume flow rates, because with change in rpm, the volume flow rates would get altered. So, this was a kind of brief discussion on the different conceptual design aspects of subsonic wind tunnel. The next thing that we will discuss is the supersonic wind tunnels. You have a rough sketch of such a facility over here. This is called as an intermittent blow down type supersonic tunnel. We will have a very brief look at it before we close this lecture. So, it comprises of a compressor followed by a dryer, which dries the moisture content of the air, because later on the compressed air would be expanded very rapidly to a large extent through the CD nozzle when it moves through the CD nozzle, and at that time the water, if any, would condense. So, in order to avoid that, we would like to have a dryer here, and then we store the high pressure air in the storage tank, and then when we want to run the tunnel, we operate the gate valve followed by the pressure regulator, and then we allow the flow into a settling chamber, which has a wide angle diffuser. That means, you diffuse the flow across a very large area ratio, and then you allow it to stagnate inside the settling chamber. Then you allow it to run through a CD nozzle, where you can see the nozzle throat, and then into a constant area test section with optical access, and finally, the flow moves through what is called as a supersonic diffuser, where you have seen the diffuser throat over here, which is slightly more extended than the CD nozzle throat that we had here. So, this is a rough structure, a schematic of an intermittent blowdown tunnel. Obviously, the heart of the supersonic wind tunnel is its test section, because we are interested to mount models in that section, make pressure measurements, other measurements, also apply optical techniques like Schlieren and shadow graph flow visualization to view the shocks, expansions forming in the flow around the model. And we also have the supersonic diffuser downstream, which we are very interested to know more about. We will discuss all this in the next lecture. So, in this lecture we completed our brief discussion on conceptual design aspects of subsonic wind tunnels with a broad overview. Subsequently, we started our discussion on supersonic wind tunnels, and we briefly looked at a layout of intermittent blowdown supersonic wind tunnel, and we will be recapitulating about the converging diverging nozzle in the subsequent lecture, and take the discussion on supersonic wind tunnel design further in the subsequent lecture. Thank you.